Alrighty, it looks like it's recording now. Okay, great. Um, there was a question on the PCCI 12.4, which I put off until today. So that one I want to do just circle back to that one with kind of one last little idea that goes with it. And then I've got two big example problems, one using the energy approach to solving problems, and one using another, like a static equilibrium. Uh, I'd say same approach as we used in our problem on Monday, but a different problem. So it's kind of more practice on that. There are a couple of practice problems in the PSS as well. I don't know if some people were there on Tuesday. Maybe this is our last official class, but there's still a problem solving session tomorrow. And I hope to see many of you there. Has anybody else joined us now? Oh, I see Elizabeth is back. Excellent. Okay, so that's my plan. And do feel free to pipe in with questions at any time. I'm going to go ahead and open up the chat window. If I don't happen to see something in the chat window, I'm counting on you, Jack, to pipe up yourself and let me know if there's a question in the chat window. The other day, people were pretty good about kind of answering each other's questions in the chat window. It's okay with me if it's a simple question. You just want to answer it in the chat window, Jack. I'm fine with that. I think that'd be great. Okay. All right. So this is our plan for the day. All right. So the big picture is that we've got a few new concepts that help us apply, like the older, I should say, maybe, concepts of how we describe motion with position, velocity, acceleration, and how we kind of explain motion using forces and mass and Newton's second law and conservation of energy or work kinetic energy theorem and things like that. We have ways now to apply that in a rotating system. And a rotating system always seems harder because it's less familiar. Things like theta and omega and alpha and centripetal acceleration, those were all things that were kind of, brand new probably to most people. So it's understandable that this one seems harder, but it's not necessarily because there's a lot of new concepts. There are a few, but trying to apply them in a rotating system just takes a bit of practice. So the big ideas that we talked about on Monday, we talked a lot about torque, and I think you did a great job with torque. And we talked a bit about moment of inertia and how to, what's the idea behind that. At the very end, talked very briefly about rotational kinetic energy and how you have to include this if you're going to do an energy approach to solving a problem. So, and I hinted that that was one way to approach problem 2 on the homework, was to use an energy approach, but also include the rotational kinetic energy in whatever energy approach you took. So we'll do an example of that because we didn't really get to an example, and I've got a nice example for us. And then the last big idea is that Newton's second law has an equivalent in a rotating system, and that is that the net torque is related to angular acceleration through moment of inertia. Excuse me. And I think it can be kind of straightforward. The torque is something that I think you were very good at, that if we're talking about the torque caused by some force, that we need to know the tangential component of the force, where it's applied, and that gives us the magnitude of the torque. And then we worry about plus is counterclockwise and minus is clockwise when we're figuring out torques due to individual forces. The really, really important thing about it is that it's important where the force is applied and at what angle it's applied, because only the tangential component of the force contributes to torque. Okay, so I feel like I missed a slide here. I know I put another, maybe it's later and I'm wrong about that. So we use this idea about the net torque being the sum of all the torques acting on an object. And then if the object is not turning, that sum of the torques had to equal 0. And this is one of the conditions for static equilibrium. The other condition for static equilibrium, of course, is that the net force, which is the sum of all the forces acting on an object, is also 0. And this is an example that we did. We did it using pretending that the location of rotation was above the second stump. You don't have to do that. And then we offered another solution which had another location. So in the case where the sum of the torques equals 0, we have a special name for those, static problems, static equilibrium problems. And we'll do another one of those examples kind of towards the end today. But kind of getting back to, I feel like my slides are not in the order I was. I'm going to go ahead and find the slide that I really wanted. Yeah, I really wanted this one first, because I really wanted to get back to that Newton's second law equivalent, which said that the net torque is equal to I times alpha. Because we already have kind of the idea that a net force causes motion. That's usually how people put it in words. In the equation that normally goes with that, it's F net equals ma. So it's really more correct to say net force causes acceleration. Okay. But often people say the net force causes motion because, if you are at rest, then a net force causes you to move. And that's kind of where that way of saying it comes from. Now, you know that when you actually have to apply it, you have to apply it to acceleration, not to velocity. So the same thing kind of happens over here with net torque, is that the normal way we would write that, tau net is equal to the rotational equivalent of mass moment of inertia times alpha, the angular acceleration. What we really should say is the net torque causes angular acceleration. And we'll see if I have enough room to actually write that out. I might have to abbreviate acceleration there. So net torque really causes angular acceleration, but if something is not rotating, then tau net, a net torque, will cause rotation. So in the sense, I mean, you'll hear me say, you'll hear any number of physicists or engineers say, oh, a torque causes rotation. Well, what we really mean is net torque causes something to rotate if it were actually at rest. If it were already rotating, a net torque would make it speed up or possibly slow down depending on the direction of the net torque. Okay, but I didn't ask this week on the homework for many problems related to like finding the angular acceleration and so on. Well, just because we got to pick 3 problems. But this one, there was a conceptual problem on the PCCI that a lot of people asked about. And I think somebody even put it in terms of equations. So if there was an equation to go with this, it's really that rotational version of Newton's second law, where if you rearrange it, the angular acceleration alpha is the net torque over the moment of inertia. So very briefly, for this particular problem, it was, all of these pictures have something in common. It's all 2 kind of point masses, 2 balls connected by a distance. And let's just refer to that distance they gave you as d, and let's define r, like the distance from the center, as being half of the distance that they gave you. And then each of these has a mass. there's a force being applied at the position of that mass, and we know the mass, and sometimes that force is at an angle. Here the angle is 30 degrees. Up here, that angle would be 90 degrees. Yeah, I think in all of the other examples, the angle is 90 degrees. So if we think about each of these, it's this the same force, the same force, same force, same force, but the direction is opposite. So their torques are actually going to add, right? Because the one on the right-hand side is going to pull that ball up at least a little. The one on the left-hand side is going to pull that ball down at least a little, or to get started. And that's going to make them go counterclockwise. So in all cases here, they're all counterclockwise. And in all cases, the force on each side is causing the same size of torque. So the magnitude, maybe I'll say, of the torque is the same for both forces in each diagram. Okay, so for each and every diagram, we can say that the net torque is, well, let's see, for this one I did down in part E, because E had the most space available for me to add stuff onto it, that net torque would be magnitude of R times magnitude of F tangential. And in this case, by drawing the triangle, F tangential is F sine theta. Okay, so that would be R times F sine theta. And you could have got to that point using another definition for cross products. Either way, you will get the same thing. And then if we were to look at every single case, the moment of inertia, we have two balls that are rotating about the center, equal distances. So in each of those cases, the moment of inertia, like for each object, is m r squared. Now I wrote tau net here, and I forgot one thing, because that force is applied twice, one on each end. So I forgot my 2. And then the moment of inertia, since I have both of those balls to take care of, I need a 2 here. So for every single one of these, we could say that alpha tau net over moment of inertia would be, let's see, the 2's are going to cancel, would be magnitude of R times F times sine theta divided by M, and I probably should not have used capital R here, that's really small r, R squared, M times R squared. And because the force is applied at the same distance that the mass is away from the center, the R in the numerator cancels with one of the R's in the denominator, and we just get F sine theta over M times R. Okay, so if we look at each one of these, the force is either 1 Newton or 2 Newtons. The distance R is either 1 meter or 2 meters. And the mass is either 2 kilograms or 4 kilograms. So if we go in there, we can very quickly find that alpha will be the values I gave here on the right. And let's just do one of those. Let's do the very first one for A. So alpha for case A, well, the force is 1 Newton. Sine theta is equal to 1 because it's a 90-degree angle. The mass is 2 kilograms. And the R, since the distance is 2 meters, is 1 meter. So we get 1/2 Newton kilogram per meter, which works out in units to be the same thing as 1/2 radian per second squared. And I will let you sort out how to get from newtons per kilogram meter over to radians, and I'm happy to take questions on that afterwards if somebody's having trouble getting those units to sort themselves out. Okay. So I wanted to make sure we got that because there were questions about this from leftover from Monday. Okay. Are there any questions about the kind of the quick review and the quick thing about angular acceleration?
I have a quick question about this stop to think.
Yeah.
So is this equation that we just derived the f sine theta over mr? Is that what you would use for solving all of these? Like part A through E?
Yes, I can certainly use it for A through E. But
Okay.
it's because of what they have in common, right? It's because the forces are always applied at the location of the mass so that those R's are the same, right? And because they're all rotating around the center and we have similar information about each one. I would not say that this is a generalizable equation here. The one that really is, I mean, the starting point, the one that's closest to our key idea is that we have to look at the net torque over moment of inertia. So if someone went through and calculated the net torque in each case, calculated the moment of inertia in each case, and divided those, you should get the exact same thing. That should not be. And so if you happen to have the force applied in a different place, then you should be able to find the net torque the way you normally would, maybe with a different R, and find the moment of inertia with the R that I used. So this would not be generalizable to other problems. So I'll write not in general, but applies here.
Okay, thank you.
Okay. Oh, that's a good question. And does anybody need a reminder about the moment of inertia? Because that's the thing I skipped over here. That was the reminder about moment of inertia was just that if you have an object that's made up of distinct parts, you sum up the moment of inertia of each part. And the big key idea behind moment of inertia is that mass that's far away counts more. So if you've got a particular axis you're going to rotate around, the mass is further away. That counts more, and you have a bigger moment of inertia than if all of the mass were really close to the center of the rotational axis. Okay? And the other thing that's a little unfamiliar sometimes is that an object has one mass, put it on the scale, there's one mass. But it has many moments of inertia, potentially, depending on what axis you choose to rotate it around. Okay? So that's just a reminder. Okay. I think we might be ready to do my energy example. Okay, so just as a reminder from the previous page that a rotating object has some rotational kinetic energy, and it's given by 1/2 I omega squared. If it's rolling, it also has translational kinetic energy, which is our regular 1/2 mv squared. So if we want the total kinetic energy, we'd better take into account both rotational and translational kinetic energy. And that's kind of where we left things yesterday. Here I have a race, which I can actually show you the race video. This is our videos that Travis and I took during the week that would otherwise have been spring break, except it wasn't really, was it? And I have two cylinders here. I'll call them 1 and 2, or maybe I'll draw that in a different color so that's a little easier to see. 1 and 2, and number 1 is 1,000 grams, and number 2 is only 500 grams. And I've got a little ruler there, and what I'm going to do is I'm going to pull up the ruler so that they both start rolling at the same time, so that I don't inadvertently let go of one a little bit earlier than the other, so the race is fair. So my question for you is, in this particular situation, I've got these cylinders have the same radius. One is double the mass of the other. They're released from rest. Which one will reach the bottom first? or will they both reach the bottom at the same time? So I want to give you a couple minutes to chat with each other about this. And I'm going to put you into breakout rooms for that. So I have a moment. So if you want to take a moment and like take a screenshot of that so that you have something to look at. I'll try not to make the screen go away so quickly. What have we got? Let's see. Let me go and see if I get this to be about, yeah, I'll make it 3 to 4 participants per room, and create some breakout rooms. And then we'll come back in about 5 minutes. When you come back, what I want your group to be able to do, and this, I really mean, I want you to talk to each other about this, that somebody from your group has to put something in the chat that says, our group thought the heavier one was going to win. Our group thought the lighter one's going to win. Our group thought they were going to come at the same time. Something like that, what your conclusion is, and then we might follow up then with what was the reasoning we used, okay? You ready for that? Okay, good. All right, so I'm going to send you there. Go ahead and open those up. Hi, how are we doing here?
Good.
Good.
For this problem, we were thinking that the one with 1 kilogram metal cylinder, we would think that it would drop to the bottom first because it has a higher moment of inertia. I was kind of like,
Oh, okay. So, so what does the higher moment of inertia? It's higher because it has more mass, right?
yeah.
Yeah, yeah. Why would a higher moment of inertia mean it can win the race? What's the link between winning the race and moment of inertia?
Because it will have more kinetic rotational energy.
Okay, so why does something with a bigger moment of inertia have more kinetic energy?
Because it depends on the the mass and the length of the object, and those are both larger for that cylinder.
Well, why would the, like, it starts out with no kinetic energy, right? But it gains some kinetic energy as it rolls down the hill, right?
Mhm.
So why would the kinetic energy that the 1 kilogram mass have be bigger than the kinetic energy that the 2 kilogram mass or the 500 gram mass have? What do you think, AC? So I'm gonna leave and let you talk about it, but definitely do talk. Don't sit in your, behind your own screens and not talk to each other about it. But you need to make a really strong case, using energy principles here, right? That, like, if you could make the case that you have more kinetic energy, then you've got to make the case that, it's going to be faster when it gets to the bottom of the hill, or something that gets you to the point of saying what wins the race, right? So I agree with you that the moment of inertia of the 1 kilogram is bigger than that of the 500 gram. I agree completely. But you've got to somehow make the case that that bigger moment of inertia makes a difference in how fast it's going, or something that you can argue, if it's going faster to win the race, for example. So if you can take that and use some energy principles to kind of fill in the gaps on the reasoning there, okay? Because it's not obvious to me that just having a bigger moment of inertia means you win the race. Okay? Okay? So Elizabeth, to make everybody talk, right? You're going to keep poking Sarah and Celine and Jasandra and make sure they talk after I leave, right? Right.
I'm good.
Yeah, okay, so Celine and Sarah, pipe up and chat. I'm gonna give another couple minutes. I'm gonna go visit another breakout room, okay?
Yeah, I feel like we could probably like solve this using conservation of energy, maybe like how we're doing that, and then like set something equal, I guess, and like maybe I guess analyze it like that. But I don't know what that would do for us really.
Yeah.
I guess to see like what the velocity is, like how the velocities are dependent on the other variables, I
You
guess.
guys are chatting. I'm gonna go ahead and to another room because you seem to be. You'll have no problem reporting back, will you? Okay.
Yeah, that's fine.
But yeah, maybe like if we know the
Radians per second. So if they have what is radian? Omega's like their units is radians per second. So that's dependent on what?
Yeah. So what are you all working on at this point? I know you're talking about omega and radians per second. But do you have like a working hypothesis of who's going to win the race and why?
So we're thinking they might end up together.
Uh-huh. They
And
might
like
end up together. Okay. And you're trying to come up with something to support that.
yeah, so like we started out was like the mechanical energy, the total mechanical energy would be conserved. So
Uh-huh.
like it was an equation for the final velocity, and
Oh,
so
okay.
like at the end, we thought like it would be dependent on like the radius and like the angular speed. So we're
Oh,
trying
okay. Yeah. Oh, okay. So if something is rolling, is there a relationship between the translational speed and the rotational speed? Like if it's a car and the wheels are rotating slowly, then the car is going slowly, right? if the wheels are rotating more quickly, right, the car is moving more quickly. So there seems like there should be a relationship between those two. Do you have any idea what that relationship might be?
I think they should be equal.
You mean the velocity should equal omega?
Yeah.
They
No.
put the same units, so it can't just be equals. But you're right, it should be proportional.
Yeah, like the distance traveled by like the.
Ah, yeah. You're thinking along the right lines.
Like a
Yeah,
full-
you're thinking about how, like, in one rotation, how far does the wheel have to travel? And I think in one rotation, you can figure out what that distance is in terms of the shape of the wheel. Okay, all right. I think you guys are probably on a good track. You're trying to relate your problem to get a final velocity, and that final velocity helps you figure out who wins a race, right? So good. I'm glad you're focused on the right kinds of things. Excellent. Okay, I'll go check in on somebody else.
Okay.
All right, how are we doing here? You're quiet.
Yeah, we kind of came to our conclusions. So.
Oh, okay.
okay.
Is it okay for me to ask what your conclusion is?
Yeah, I just put in the chat, but basically we think that the two cylinders reach the bottom at the same time because the difference in mass and the difference in moment of inertia between each is proportional, so they'll have equivalent kinetic energy. So one has twice as much mass, but also twice as much mass away from the center, so thus an increased moment of inertia, and the other one is half as much mass, but then of course half as much moment of inertia, so they'll essentially be proportional.
Oh, okay.
Yeah.
All right. Sounds good. I'm gonna check in with one more group, and then probably you can go back to the main room whenever you're ready. I'll probably call people back in a minute or two.
Okay.
Like clear whenever.
Hi there. I see Jackie and Angela. Sorry, you're just two to a room.
Joyce is in here too.
Yeah. I'm like, no, that's not me. That's the other Joyce. Maybe at Joyce's house, I'm the other Joyce, right? Yeah. So have you all have an idea about what who's going to win the race? What's your?
We're trying to find the angular acceleration to see which one accelerates faster.
Oh, okay. Oh, okay. That might be a little tricky, but
Yeah.
yeah, because rolling is actually a tricky one to do with forces. It's less tricky to do with energy, and I see you do have an energy equation out there. What kept you from going further with that energy equation?
Would we use the like the KE initial plus and like gravitational potential initial equals KE final plus gravitational potential final?
Well, that would be basically using conservation of energy, right? And would that apply here? I mean, is there any reason why it wouldn't apply? What do we look for?
Don't necessarily know anything about the gravitational potential.
Oh, you don't. Yeah, well, you don't know exact numbers, but you certainly know they both start at the same height and they end at the same height.
Oh,
right?
I see.
Yeah, so you don't know a number, but you certainly know. I'm trying my best to get them to start at the same place without giving either one a favor. So you certainly know they start from the same height. So I think you could argue they start with the same potential energy, or at least the same height, right? And then, since it doesn't seem like these things are rubbing, there doesn't seem to be kinetic friction here. It's rolling, so maybe let's neglect friction. For neglecting friction, then conservation of energy would be a valid approach. Okay.
Okay, yeah.
All right. Okay. Well, I'm probably going to call back everybody to the room in a minute, and you may or may not have a full answer, but try to come back with some idea of which one you think is going to win the race for some reason. But you're kind of going in the right direction here. Thinking if you had found alpha, then that would have been one way to tell. But it might be a little tricky to find that because rolling is a little bit tricky with what being caused by static friction, essentially, and gravity interacting. So, okay. All righty. Then see you back in the main room at some point. I'm going to go probably check one more group.
Okay.
Okay.
Thank you.
So, okay, so if you like the equation and so
Wouldn't it have a greater translational because it's moving at a greater speed because it's rotating faster?
I don't know. Would it?
I'm going to say yeah, probably.
So I'm looking around, I'm finding not all groups have come to a conclusion yet, but I might bring everybody back to the main room. And I was going to ask Jack, what do you think of that? Think it's time for people to come back?
Yeah, I think so.
Okay, all right. So I'll go and send a message to the breakout rooms and tell people to come back. Okay. Okay. I'm seeing people coming back to the main room now. Okay. So I heard a lot of great questions and some discussion, and in many rooms I found people just trying to figure out, oh, how do I even get any information that's relevant to how to win the race. So oh, I lost my chat box. Okay, let me open up the chat here. So can everybody see? I think Melissa put something in the chat room for her group. So from your groups, go ahead and put in like what your best, I don't want to say guess, but your best thoughts about either if you think you know who's going to win the race, put that in, or if you like got to the point where you had a question, or you got to the point where you're like, I'm sure this is the way to do it, but we didn't finish. That's put something in the chat room about what you all thought. Okay, so what I'm seeing is from Melissa's room, was breakout room 4, says that it's going to be a tie. They're going to reach the bottom at the same time. Joyce's group, which was room 5, were setting up the conservation of energy equation, and they hadn't come to a conclusion yet. Heather says the 1,000-gram mass will reach the bottom of the ramp first because the mass has greater inertia and greater moment of inertia, right? And the greater rotational kinetic energy because of that, okay? In Serena's room, which was room 6, they were unsure, but they think maybe since the larger mass has more potential energy, it might reach the bottom faster. Okay. Well, those all sound kind of reasonable. That, more potential energy you start with, then you might have a faster velocity at the bottom because that would be more kinetic energy at the bottom. Another one from Theo's room, which is this room 3, they agree with room 4 that they'll reach the bottom at the same time. And she says because the final velocity is independent of mass and length. Oh, so you must have gotten a little further on that conservation of energy equation. And was that, Theo, that the masses all canceled out and the radius of the thing all canceled out? Oh, okay.
Yeah.
So when you solved it, all those things canceled out. From Serena's group, they weren't sure if they could relate the tangential velocity to omega by v equals omega times r. Oh, that's really a critical question, isn't it? Because that's actually really important to be able to do something, something that's easy to interpret from the conservation of energy equation. So yeah, so we definitely would talk about that. And in Chloe's group, it sounds like the same kind of reasoning that Heather said, because they have, total mechanical energy is higher. Okay, good. Well, let me go over to share the screen, because I think addressing what Serena asked about, sorry, who was it? Whoever asked about V equal to omega r. Yeah, I guess that was Serena. So I'm going to share my screen for that, because I think there's a pretty straightforward way to understand that. Oh, there's my share screen button. And there's my iPad. And there's my share. Okay. So, and where is the chat now? Okay, so I'm not seeing the chat. I might rely on Jack to holler when something is in the chat. So that question about omega, I'm going to add an extra slide in here. So here's the deal, right? If something is rolling along, and maybe I'll make it a darker color. If we got a wheel that's rolling along, right? I mean, we all kind of have the idea that, from cars, from any kind of wheeled vehicle, right? If you're trying to go fast, translationally, say on a bicycle, the wheels on the bike have to roll faster, right? So there's some idea that probably your intuition tells you that the velocity, the translational velocity, like the velocity of the center of mass point here, should be at least proportional to omega for the wheel, in the sense that if the wheels are going faster, the velocity is going to be bigger, right? The wheels are going slower, then the whole thing slows down. So it should be proportional. So let's do a thought experiment. And I'm going to take this little location on the wheel. And now I'm going to have that wheel roll over to the right, since I have that velocity of the center of mass point sitting there. I know it's rolling to the right, and I've got omega here written such that it would be going again to the right. So after a while, once it'll move a little bit, and I'll just dot this one in. At some point, you've rolled enough, you've made a half of it at a half a turn. That dot is up here, and then keep rolling, and later on, that will have rolled down to the bottom again, right? So in one revolution, right, that would be 2 pi, radians is how far it's turned, right? And in one revolution, it's also gone a distance. Well, what is that distance, right? That distance means that, each little part of the surface had a chance to be in contact with the road. So the distance traveled is equal to the circumference. And that's supposed to be u, which would be 2 pi r. So if the velocity is such that they went 2 pi r in some amount of time, and omega would be it went 2 pi radians in some amount of time, then it must be that v is equal to r times omega, because 2 pi over t, this is just omega. So your intuition saying they've got to be related, and we used v equals r times omega before, that actually works. That actually works here for rolling as well. So that is actually very, very helpful. Does that change anybody's minds about whether they, who wins the race? It seems like we're between one group saying they tie, another group saying that the heavier mass gets there faster because it has, essentially because it has a bigger moment of inertia, right? And I'm going to do my best to try and find the chat. I found the chat room, the chat box. Okay. So let me see what I'm seeing in the chat room. Melissa says this solidifies her group's opinion, or at least her opinion, since she's maybe not, depending on if she's chatting with her group as well. Does any other group have a change in opinion? So what I think I'd like to do then is, what I'll do is this. I'm going to put a link in the chat. And it's a link to the place where the videos are. Because with this many people, it's hard for me to show a video and have it come out okay. But I just put a link to the place where the video is. And it's the very first of a number of videos there. So go ahead and take a look at that video right now. Give you a minute to go look at that and watch that video and tell me what the actual result was. Let's go. All right, so I'm not hearing a lot, maybe because people are muted. Okay, so tell me what you see in the chat box. Yeah, I'm seeing a lot of people saying they tied. They tied, and they sure did tie. And that's, that was a very reproducible result. It was not difficult to make that video and get it to work again and again and again. So good, I'm happy you're seeing that they do land at the same time. And I don't think that this is obvious. Something I heard in more than one group was this idea that a bigger moment of inertia would help you. So does anybody have an idea about why is it that a bigger moment of inertia doesn't really help? And maybe looking at the clock, it's going on 2. So I want to make sure we have enough time for the statics question. I think the idea of that a bigger moment of inertia will give you a bigger velocity is this idea that the kinetic energy is proportional to, well, it's equal to 1/2 I omega squared. So we're always thinking, oh, if I is bigger, and sort of in the back of our minds, we're thinking omega is the same. But you couldn't necessarily count on omega being the same, right? So instead, if we look at, because there is a constraint on that kinetic energy, and that constraint has to do with, well, how much potential energy do you have to start with? So if we have something that starts out here with V equals 0 an omega equals 0 initially, and it has whatever mass it has. And then down at the bottom, it has a V final and an omega final that we don't know what it is yet. It starts out here at a height, however high up that hill we start. So that its U initial would be mg, I'll say h, and then as soon as I say that, I've got to say y equals 0 at the bottom. So down here, U final equals 0 because it's mg, y, and y equals 0. So if we set up that energy equation, we get that K initial plus U initial equals K final plus U final. And initially, because it's not moving, V equals 0 and omega equals 0. So both rotational and translational kinetic energy is 0. Let's see, on the final side, the final kinetic energy is 0. So we're really looking at that similar, very similar to a problem we've done before where something was sliding on a friction-free surface. So over here, I have mgh, and I've not yet specified which mass I'm talking about. And then for K final, I've got 1/2 mv squared plus 1/2 I omega squared. Yeah. So one thing you can probably see here is that even though they both, I mean, you can surely say that the heavier one has a bigger moment of inertia, but because they start at the same height, it also has a bigger potential energy to start with, okay? And maybe those two things might kind of cancel each other out. We'll see. But this would be a really convenient place to say this omega, oh, I forgot to put the subscripts in, that omega final would have to be the same as V final divided by R. And that's the radius of our little ball. And I'm going to use capital R here for the radius of the little ball. And the moment of inertia for these are both basically disk shapes. Anybody happen to remember from homework or from that chart? The chart tells us that if we look it up on that chart we used yesterday, that the moment of inertia for a disk is 1/2 m times r squared. So we can rewrite this right-hand, oops, sorry, I didn't mean to do that. Let me go back, how do we go back? There we go. And let me turn off that particular feature. Okay. So I get 1/2 m v final squared plus 1/2 times the moment of inertia, 1/2 mr squared. And then I've got to multiply it by omega squared, so it'd be V final squared over R squared. So the R's actually cancel. So I think this is what someone referred to in the chat already, is that the R's cancel out. Yeah. So great. And this is still MGH on this side. So now I would argue every single term has an M in it, right? So M, I didn't mean to do that. So the masses can cancel out here. And both of these terms have a 1/2 in front. So I'm going to multiply everything by 2. So I've got 2GH is V final squared plus this 1/2 MR, so there's a 1/2 in there. I'm going to go ahead and I'm going to call this 1/2. I'm going to treat it special. I'm going to call that C. And I'm going to call that C the shape factor for a disk. Okay, the shape factor for a disk. Because remember in that chart, if you had a disk, then the moment of inertia was 1/2 mr squared. But if you had a sphere, it was 2/5 mr squared. And if you had a hoop, which would be like a hollow disk, then that was just mr squared. And I'm thinking that this, whatever this prefactor here is in front of the mr squared, or here it's a 1, I'm going to call that C, and I'm going to refer to that as the shape factor. Okay? So I've got 2, back down here, 2G8 equals V final. And then I took, and so I've got my C times V final squared. I changed colors. Let me go back to red. I like that a little bit better here. So 1 plus C times V final squared is 2GH. And then V final would be square root of 2GH divided by 1 plus C. Okay. So we have a nice expression there for the final velocity just based on energy principles. And it does look like the mass itself doesn't matter. But that kind of makes sense because everything was proportional to mass. In the end, the rotational kinetic energy, the translational kinetic energy, the gravitational potential energy, all of those depended on mass. So the mass itself didn't matter. It does seem like the final velocity might be affected by this shape factor in some way. So for the next problem I'm going to ask you about, I'm going to recommend you either take a screenshot, or if you've got notes, definitely make note of that V final and make note of the shape factors for various things, okay? And I want to just give you another problem like this, and just to make sure we're all on the same track. I've got another video actually at that same link where the two objects are not quite the same. This one is hollow. So this one is a hollow tube. I think the word Travis used when he made it, he called it a pipe. Right, so I've got a hollow tube, and this is that same disc. This one is 500 grams. The hollow tube, because it's longer but it's hollow, this one is also 500 grams. What if I erase those two? So there, I'm going to do the same thing. I've got my ruler set up there so that I can let them go at the same time. My question for you now is, which of these will reach the bottom first, or will they both reach the bottom at the same time? Okay, so I'm going to send you back to your breakout rooms as soon as I find that. There we go, breakout rooms, and I believe it's got you all set up in the same breakout rooms. So I'll open those rooms and give you about 5 minutes to tell me who do you think is going to win the race, and kind of why. Okay, and I see Elora, you must have. Yeah, which room were you in?
6.
Room 6, okay. Let me send you there.
Thanks so much.
Sure.
Because you remember the final velocity from the last problem is square root of 2 times g times h over 1 plus c.
Yeah, and so so the denominator is larger than, or no, the denominator is smaller.
Yeah, because it's just half of it, half of m times r squared,
Oh, okay.
I think.
Okay. I'm hearing people
Would we still,
chatting.
would we still set up a conservation of energy equation to try to also figure this out?
Yeah, we can.
Yeah.
I think if we already have like the final velocity
Okay.
Yeah, but I
set
think
up,
the setup is gonna be really similar.
Yeah, that's what I'm assuming too. Because I'm thinking, I feel like the hollow shape would actually make or break whether or not it would be faster or not. But I'm
Yeah.
still trying to think about how it would, if that makes sense.
well, I think like when we're given like the shape factors,
Yeah.
it's like they have different like coefficients, and that just like affects how.
The solid would go first.
Yeah, because it's got the if it has the smaller factor in the denominator, that's gonna mean a bigger velocity.
Yeah.
Hi, how are we doing over here? Have you got a conclusion? Which one will win, or will they be the same again?
Oh, that the cylinder will touch first.
The cylinder will touch first rather than the hoop or the pipe, as Travis was calling it. Okay. And do you have a way to explain that with some physics principles?
Was using the same equation and using the
No.
the denominator and what's in the denominator determines what's going.
Yeah. Can you think of a way to explain it without using the equation that would make sense to somebody who maybe wasn't that good with equations, but was pretty good with things like, well, if this gets bigger, then that has to get smaller, and that kind of thing, right? So if you can think of a way to explain it that way too, that would be great, because it sounds like you've got your heads wrapped around the kind of the solution to that energy problem pretty well, and how moment of inertia affects that actual equation. But if you can try to make a more general explanation, if you can, okay? Think about how that moment of inertia affects different kinds of energy terms that end up in this equation. Okay?
Okay.
Great. And I'm going to go check in on another group.
I think I just wanted to take thermo first. Hello.
Hey. So have you all decided who's winning and why?
Yeah.
Can you explain why in terms of something other than the equation's denominator is bigger for one or the other? Or the equation's denominator is smaller for one or the other?
Shape factor.
Yeah.
Shape factor, right? Right.
Yeah.
But can you think of another way of saying how does that, like, why does that shape factor, like, what energy terms is it affecting, and how does it affect those energy terms? Right? Because most people, when you talk about energy, they kind of have an idea of what it is. But if you go to people and say, "Ooh, shape factor," they're going to go, "Shape factor." Ooh. But I claim there's a way to think about this, and it would help you with assessments, by the way. That's one thing it can do. And think about how does the shape factor affect the way energy is apportioned into the different energy bins we have. You know, we have potential energy, we have rotational, we have translational, kinetic energies. Think about how it affects how that energy gets portioned out, and see if you can come up with a way to explain who wins the race kind of from a bigger picture, because it's clear that you've got how to do it with the equation, which is good. And you understand how to use that shape factor to actually think through who's going to have a bigger velocity, which is great. Okay? All right, I'm going to go to another room.
Well, this is, I could think of it in terms of like playgrounds.
All right. So I'm not surprised to hear it's quiet here because you guys have kind of solved it. The same thing I had written out. You probably have something very similar, right on your own sheets. So my question for you is, can you think of how to give a more general explanation of like, why does the shape factor do this? Energy, and without, like, maybe even without using the word shape factor.
Sure. Well, I think that the shape factor has more to do with the moment of inertia. Well, it is part of the moment of inertia. More specifically, the shape factor has to do with compensating for the amount of mass that is closest to the center of mass. So if you have more mass away, in the case of a tube, then it's kind of a larger shape factor, and that's a larger moment of inertia. Whereas if you have a smaller shape factor, and that's a smaller moment of inertia in the case of a disk, assuming an equivalent R, then you will inherently have a smaller moment of inertia, and thus you'll end up having less rotational velocity, or less rotational velocity or kinetic energy, and more translational.
Okay, I would agree on the kinetic energy. I wouldn't agree necessarily on the velocity, but it depends on what you're comparing it to. So I take that back. I think you're, okay, good. So I'm asking a lot of people to come up with explanations like that. So hopefully we'll hear a few when we get back to the main room. I'm thinking it might be time to come back fairly soon. I'll check with one more group, maybe, unless Jack has checked with everybody. I'll check one more room and then I'll call us all back. So you go back whenever you're.
People posting for the first problem. Hey, Joyce.
Oh, hello.
So you've got a prediction for this one? Okay.
Yeah.
So when we get back to the main room, which will be just in a minute, I'm going to ask about, could you explain this in another way other than this equation? Because there is a way to think about it that you could probably explain this to, any reasonable person who kind of knows what energy is. Or say you could explain it to your former self before you got to chapter 12 about how it would work, okay? So you can think about that. How does that, without using the word shape factor, I would say, without using the word shape factor, you can actually explain this fairly easily if you, and you would need to know moment of inertia. Okay, so your Monday self who understands moment of inertia and and energy considerations, okay?
Okay.
Righty. So send people a message now. Okay. Good, very good. People are coming back. Alrighty, it's about. We should be wrapping this up soon because it's about 2:15, and I want to give us at least 30 minutes with the other statics problem. So what I heard in all the rooms I visited was that actually maybe I should just ask. Put it in the chat box. Which win the race? And then I'd say, if you want to, go watch the video. At that same link as before, there's another video, and you can actually see who wins that race. So, okay, now I've got to find how to get the chat box going. There we go. Okay, so looking here, I'm seeing the cylinder, the non-hollow one, the solid disk. So we seem to have a consensus among all the groups that it's going to be the solid disk that wins. Has anybody taken the moment to watch the video? Yeah, I see a couple of people watch the video. Okay, good. So it does, and it consistently does. That's not a hard experiment to do well. So I think I sort of set you up for an explanation where you say, well, we have an equation for V final, and it's got this shape vector C, and I know the shape vector for the hoop is bigger than the shape vector for the disk. So you can see, what does a bigger C do to this? A bigger C makes the velocity smaller. So since the hoop has a smaller velocity, it can't win. The one with the higher velocity has to win. So it'd be the one with the smaller shape factor, right? So I think that that was the one I sort of set you up with. Did anybody think of another way to sort of think about it in terms of, you know, where's that energy going? And then they all start out with this. In this case, since the mass is the same, they start with the same amount of potential energy, right? And as they roll, how come one of them gets to go faster than the other one? And you can do it thinking of it in terms of moment of inertia, or you know, how that energy gets kind of sorted out. Does anybody have a way to think of it where we don't have to ever use the word shape factor? I saw some heads nodding up and down. Did I see Piper's head nodding up and down? No. Oh, okay. Oh, that's definitely side by side right now. Okay. Does anybody have an idea of how you might think about that?
Oh, sorry, go ahead.
Okay, I was gonna say that I'm thinking that maybe the other one would have more rotational energy since it
When you
has
say the other one, now I'm going to ask you, which one do you mean by the other one?
the hollow one. The hollow one, like
Oh, the hollow one. Oh, okay. All right. I'm going to go ahead and share my screen, so I'm going to kind of take notes on what you're saying. Okay. All right. Go on. So there's the disc. Oh, I don't want yellow. There we go. There's the disc. And there's the pipe, the hollow one. Okay. And you said something about the hollow one having more of something?
Sorry, I'm thinking that it has more of the rotational kinetic energy. So like more of its energy goes to being to the rotational kinetic energy rather than
Oh, okay.
the rotational one.
Okay. So they both start with TH, with the same amount of U, right? And that U gets transformed into regular kinetic energy and rotational kinetic energy. So this one is the 1/2 mv squared, and this one is the 1/2 I omega squared. And for this one, if you have a bigger moment of inertia, you're saying it kind of more of that potential energy has to go towards making it rotate.
Yeah.
Okay? So
Yeah.
bigger I really means more U is transformed to rotational kinetic energy. That's supposed to be a K rotational, right? Because, well, I is bigger. Okay, so if something's bigger, it actually takes more energy to get it rolling to the same speed as something where the mass is close in. Oh, well, that makes sense. So if the having a bigger moment of inertia means more energy is going transformed this way and less energy is transformed over here to mv squared, and v squared is what wins the race, right? V wins the race. Omega, any energy you have to put into rotation is energy that doesn't help you win the race. So in a way, you can think of it, well, if it has a bigger moment of inertia, I'm wasting more of my energy trying to get this thing to turn around. And if you have a smaller moment of inertia, you're wasting less of your energy trying to get it to turn around. Okay? So I remember talking to at least one group where they said, you know, this is about the moment of inertia. And I think it is about the moment of inertia. But it wasn't necessarily its absolute value. It really was kind of relative if the mass was mostly out at the rims or if the mass was more close to the center. Has anyone seen, there are some well, interesting high-end bicycles, and there are some where they make the wheels be more like discs and less like a normal bicycle wheel, right? There's a trade-off. You have more mass, of course, if it's a disc than if it's just a rim. But you would then proportionally spend less energy rotating those up if the mass is more evenly distributed and not all at the rims. So that comes up in a couple different kind of situations. So very good, very good. I think we've kind of done this one to death. There are a couple of other videos on there that you might want to take a look at with another hoop race. There's one where I've got a sphere versus a solid cylinder. That one had kind of a funny outcome. And then there's another one about I've got a hollow wooden cylinder and one that's full of seeds. Okay. So Jack, what do you have to say
Yeah,
there?
so I think Theo, do you have your hand raised?
Yes.
Oh, absolutely. What's your question?
Yeah, so I wanted to know, like, if there is a different like reasoning, like a different explanation without using C, like in order to identify like why the hollow one will have a higher inertia. Like, what is the reason behind? Like, what is the
well, you have to do something at least that explains the same thing as C explains, right? And C is basically telling you how big is the moment of inertia. How well, I mean, is the mass distributed far away from the axis of rotation or closer in, right? And so for the hoop, it's further out. And it's so if you were to talk to somebody who understood that, oh yeah, moment of inertia counts mass that's far away more than mass that's closer in, you could certainly say, yeah, I've got a moment of inertia is big. It takes more energy to move all of that mass when it's far away, because you've got to actually, each little bit of mass, it has to get up to speed, and you have to give it that energy to get up to that speed. But if it's a disk, the pieces of mass that are closer, they're not going as fast. The ones that are close to the axle, they don't have quite as much kinetic energy as those ones near the outside edge. So for that hoop, like every single molecule has to get up to the same speed. That would be the same as V final times R. Yeah, V final, sorry, divide by R. Every single molecule has to get to that speed. But for the disk, the ones that are close to the axis of rotation, close to the center, they don't have to go that fast. So they're not kind of, I hate to use the word suck out, that sounds really bad, but they're not sucking out that potential energy and using it to just spin the thing. It's using that energy to translate it. You know, it's available then. So that's another way to think of it without necessarily using moment of inertia, but certainly thinking of it in terms of how much energy it takes to get little bits of mass to move. Does that make sense?
Yes.
Okay. Okay, very good. So are we ready to go on, or are there some more questions regarding this? Okay, at the moment I'm not hearing any, but I don't see the chat. Is there anything going on in the chat, Jack? Nope. Okay. All right, so let's move along, because with statics problems, it's really practice, 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 as Professor Wilkov used to say. So I told you about the other posted videos. Here, I've got a statics problem. I've got here a picture of a ladder, and I know the length of the ladder, and it's leaning against a wall, and we're going to treat this wall as having no friction. That's just really a simplification here. The coefficient of static friction between the ladder and the floor is known, and that's given in the question. So the question here is, what's the minimum angle that the ladder can make with the floor without slipping? And I've got that labeled here as the angle here between the ladder and the floor. Okay. And I started this off because I found a nice picture of this in your text about which has got what you might call an extended free body diagram there. It's got all the forces labeled. It's got the angle labeled. It's got everything in symbols, which, you know, that's what I really like, is everything in symbols. So if we're going to take the approach of statics, which is kind of a change in gears from what we were just doing with energy, what are the kind of the important things that we would need to keep in mind when we're trying to solve this problem, assuming we're trying to do it with the key idea of static equilibrium? Yeah. What's one of the starting points that you might want to use for this?
The summation of forces in the x and y direction must equal 0.
Oh, okay, okay. So in a sense, it's like Newton's first law. The net force equals 0, and that's F net x and F net y. Oh, it just barely fits there. Okay. What other things does static equilibrium mean now that we know more than just forces?
Net torque is also 0.
Okay, so I would call that rotational. Newton's first law would be net torque equals 0. So, and well, we don't have more than one axis, at least not in the problems we're going to do here for the net torque. We're only going to have one axis that this could rotate on. Okay, all right. So with that, I'm trying to think. We have enough. We only have half an hour, so it might be hard to get a lot of results with if we go to breakout rooms. But what if we do this instead? I'm going to have to set up equations based on these net force in the x and y directions. Would you be willing to shout out the terms that belong in the equation? And we'll just kind of solve this together as a group of 25. Would you be okay with that? Okay. Alrighty. And I'm just going to, I might call out names. If I call your name and you don't know what the next term or another term would be, you can say pass. Okay. So Anna started us out with the sum of the forces in the, I'll say the x direction, equals 0. And Elora, what's one term that should be in that sum of the forces in the x direction?
N2.
N2? Okay, yeah. N2, and since it's going to the right, that should be positive or negative?
Positive.
Positive, okay. Grace, what's another term that should be in this one?
Static friction, which will be negative.
Oh, okay, all right, okay, good call. Before I write the positive sign there, minus Fs. Maggie, are there any other forces in the x direction?
Is N2 in the x direction? I mean, no, not in the x direction, sorry.
Okay, so we're done in the x direction.
Yeah.
Okay, great. Hang on, because you get to do the first one in the y direction. What's one of the forces in the y direction?
N1.
N1. Okay, great. And then Serena, what's another force in the y direction?
The F grab for the ladder.
Uh-huh.
And I think that'd be negative.
Okay, so minus. And I'll call it mg. There's only one mass here, right? So I only have to give it a subscript. Okay, great, great. Heather, are there any other forces in the y direction?
Sorry.
Okay. All right. So I saw your mouth say no.
I,
Okay. All right. So we're done. We're done here. And if I look at these equations and think about what do we know and what do we not know, it seems like we don't know any of these, right? We don't know N1, we don't know N2, we don't know the force due to static friction, but if we knew N2, we might know it, right? I'm sorry, N1. If we knew N1, then we could say, oh, we'll know at least the magnitude of that static friction force, right? Because we know that at, like, when it's about to slip, that Fs would be mu k times the normal force, and that would be M1 because that would be right at the same location. So maybe I shouldn't treat the static friction force as like an extra thing we know. We would have to find, but we don't seem to know the mass either. So mg, that term, we don't know that term. So we've got at least 1, 2, 3 unknowns here. We only have 2 equations. We need something else, clearly. And what Anna mentioned at the beginning is that maybe we should sum up the torques and set those equal to 0. Okay, so Heather, before I leave you, we're going to do a sum of the torques. We had better figure out what axis of rotation we would like to use. And for a statics problem, since it's not rotating, we can pick any location we want to be the rotation axis. Do you have a preference? Like what location on the ladder we use?
I guess we could, I think, like the in the figure it says T net equals 0 about this point, and then it points that there's like a black.
Uh-huh. Oh, okay. So your text suggests using this point, and they made a big black point. Yeah. Okay. And you're thinking the guy who wrote this text, pretty smart guy, he wouldn't have put that there unless that was a good idea. Okay. Yeah. All right. I think I'm happy to use that one because it turns out that one's the easiest. And the reason it's easiest is what he wrote in the fine print there was that 2 of our forces, static friction and 1 of the normal forces, are acting right at that pivot point. If we choose that, if we choose that to be our pivot point, then those will have no torque. So that means, oh, my torque equation is going to have 0 for the torque due to N1 and the 0 due to the torque due to the static friction. So anything that will make there be fewer terms in the torque equation is all right with me. Okay? So great. So Heather, you've done all the work you need to on the torque equation. Let me go over to Piper. Piper, do you have a candidate for one of the terms that should be in the sum of the torques?
I guess the torque at theta, right?
You say the torque at theta caused by what force?
The force of, I guess, gravity and friction.
Gravity and friction? Just pick one. Pick one of those, because the torque equation is going to have 1 term for every force.
Yeah.
So I'm only asking you for 1.
Then just static friction.
Okay, well, the force due to static friction is right here, and it's acting right at the location of the pivot. So the torque due to friction, how big will that be?
So if torque is the magnitude of R times that force.
Uh-huh. And then R was what?
Yeah. D1.
D1?
Mm-hmm. Times, oh yeah, force of static friction.
Well, what's the R was the distance from where to where?
I thought that R would just be the distance along the x-axis from the point where theta is to the center of mass of the ladder.
Oh, no. Yeah, so let me go. Actually, I think there's a slide at the beginning that talks about it. Is that this R, this is always the distance from the axis out to the location where the force is applied. Okay, so R is from the axis to where the force is applied. So let's go back. Right, there we go, fine. So what's the distance between our axis of rotation and where the frictional force is applied?
They're applied to the same point.
Ah, so that R, how long is that R?
0.
0 equals 0. Okay, excellent, excellent. Let's see, next up, Jackie. Can you give me another term that should be in this torque equation? And you can give me one that's got to equal 0, but you're gonna have to tell me why.
Another force that would, or another torque that would be 0 would be normal force, the first.
Oh, okay.
Normal force
So
1.
plus the torque due to normal force number 1, and that one is 0. Why is it 0?
Because it's, it comes R0.
Yeah, because R is 0. The same exact reason why friction was. It was by Heather's very clever choice of axis of rotation that we got two terms that equal 0. Okay, all right. So let me go next. I see Theo's lovely face. Theo, can you tell me one more term that should be in this torque equation?
Gravitational force.
Oh, okay. So the torque due to the gravity.
Mm-hmm.
Okay. And what will that one be? I'm going to go ahead and carry that one down. How big would that torque term be?
So it would be force applied due to gravity times d1.
Okay, so the force due to gravity, so you're saying, so it's magnitude of the force due to gravity times, and you're saying d1. Okay, I think that is correct. Fg times d1. Did anybody else think of something else to put there?
Maybe.
Yeah. There would be another way to do it if you used R times F tangential, and you broke this into a tangential and a one that was along the axis. That this, I'll make that bigger so it shows up a little bit better. That Ft would be mg times sine of theta, and then you'd be multiplying that times L over 2. Okay, so there are two terms that will work here, but since Theo said Fg times d1, then that is perfectly fine. The reason that they're equal is that if you look at it, L over 2 is the hypotenuse here, and if this is theta, oh, now I'm wondering if I wrote the wrong one, sine instead of cosine. Let me, oh, yes, I wrote the, that's not sine, that is cosine. Sorry for that. Cosine theta, that d1 is actually equal to, in this triangle here, d1 and L over 2 is the hypotenuse. So either of those two terms would have been acceptable. I'm going to write it the way Theo said. Okay, so the torque due to gravity, and is that positive or negative? Is that clockwise or counterclockwise?
Yeah, it's going to be counterclockwise, so it would
Okay,
be positive.
so I leave it without putting a minus sign.
Mm-hmm.
Okay, Chloe, you're up next. Can you think of one more term for our torque equation?
I'm thinking about the torque applied by N2.
Oh, okay. So torque applied by N2. Okay. All right. So, and yeah, so how big would that torque applied by N2 be?
I think it would be like find the force perpendicular to
okay,
the ladder.
Okay, so you'd like to break this N2 into a force that's perpendicular, and its other component would be along, but we're really interested in the perpendicular component. Okay, so if N2 is this way, and it's got like a right triangle like this, if that's N2, how big is this component? Which of those two angles is theta? The one towards the left, the one towards the right?
Right.
Okay, I'm saying this one, yeah? That one's theta? Yeah, because this one over here is 90 minus theta, okay? And since this N2 is normal to the wall, this angle here would be theta. And then if I'm looking over here, those two are perpendicular, so this is 90 minus theta, and that's the same as this angle here is 90 minus theta. So theta is this angle over on this side. So if we wanted to get N2, the one that's perpendicular or tangential, what would that be in terms of N2 and theta then? Would it be sine or cosine?
Sine.
Okay, so N2 sine theta. And there's more than one way to get to that result. But so we've got that perpendicular, and then what else would you like to use to find that torque term?
So if it's like N2 sine theta, that would be times L, which is the distance to the pivot point. But if it's like L times sine theta, would also be D2 in this case.
Okay, I'm going to go with your because we already did the thing about the tangential, so we'll go ahead and say L here. Now is that counterclockwise or clockwise?
Clockwise.
Clockwise. So I'll put a negative sign here.
Yeah.
Okay. All right. And you were kind of pointing out that there's a relationship between D1 and L. Right? And then maybe we'd like to put our equation in terms of just one or the other of those. And so using the big triangle, I'm going to do this off to the side. If this is L and D1 was just half of this side, so this whole side here is 2 times D1, and our angle here, that's our angle theta. So twice D1 is L times cosine theta. So we could put that in there. We could either solve for L and substitute in for L, or solve for D and put in for D. Since D is already on this side, I'm going to say, well, let me substitute this way. So I would get FG times D1 L over 2 cosine of theta minus N2 times sine of theta times L, little skinny L in there. Okay, and all of that equal to 0. The sum of those two equal to 0. So now let me kind of reassess things. I have a third equation now, so I've got 1, 2, and now 3 equations. Okay, we know the length of the ladder, so that's not introduced in something we don't know. And N2 and FG were already in our list of unknowns. So I argue right now we have 3 equations, 3 unknowns. So this problem can be solved. Okay, shall we try doing that together on the next page, or should I leave this to you to solve the 3 equations, 3 unknowns? Are we looking for closure here today? Maybe if we're looking for closure, then we might need to, how do I do this in this mode here? Yeah, I'll make myself some more room by doing this. So I know it makes it a little bit smaller on your screen, but that'll just give us enough room to finish up my 1, 2, 3 equations, 3 unknowns. Let's see. I'm not sure there's going to be a fast way to do this. Does anybody see like a quick and easy substitution that I could do to get, to say eliminate something? If I'm trying to find, what are we trying to find again? We're trying to find theta. Okay. Is there anything we can do here that would get rid of some things?
Maybe like solve for n2 and then substitute cos theta over sine theta was 1 over tan theta.
Okay. All right. So if we solve for n2, okay, I'm good with that.
And cancel out L.
Sorry?
And that can also cancel out L for us.
Okay. All righty. So I don't know if I'm following exactly what you're saying, but let me just summarize what we know here, over here. That N2 has got to be the same as the magnitude of static friction, but we know the magnitude of static friction right at the point where it's about to slip is mu s times n1. So in any particular equation, n2 and n1 have a pretty straightforward relationship, and we've kind of eliminated static friction from the equation, right? The second equation says that n1 is equal to mg in magnitude, right? Oh, okay. Well, then let's go up here. Mu s times n1. N1 is mg. Okay, so we've solved for n2, at least in terms of mass. Okay. So now let's go to that torque equation. We know that Fg times L over 2 times the cosine of theta has got to equal N2 times L times the sine of theta. Yeah. And we've got that Fg has got to be mg L over 2 cosine theta. And that N2 was US mg, and then we still have to keep our L sine theta as we go along there. Mass cancels out. Thank you. L cancels out. Nice. Not necessarily expected. G is on both sides. G cancels out. So I've got cosine of theta over 2 is equal to mu s times sine of theta. Okay. And let me take this over here where I have a little bit more room. Okay. We got sine and cosine on different sides, but if you take the cosine and put it underneath the sine, then you could change that into tangent and it'll look simpler. So I'm going to multiply both sides, divide both sides by cosine, so that I've got sine of theta over cosine of theta. And then at the same time, I'm going to divide both sides by mu s, so that I get everything else on the other side. Okay, it would be equal to 1 over 2 mu s. And since this is equal to tan theta, I think we can get theta is the arctan of 1 over 2 mu s. Yeah. And then whatever else they were to ask you about this, we could probably find from them. We might need to know the actual mass to get the actual size of the normal force, but we didn't need that to solve just for the angle. But if they told you the mass, now that you know the angle, you can find all of those normal forces as well as the static friction force. Okay? And does that answer make sense? Does that answer make sense? Well, let me ask you this. If the floor were more slippery, meaning mu s would be smaller, would you expect that the ladder, that the angle that the ladder could possibly have would be even smaller, or would it have to be bigger if the floor is more slippery? Right, so if the floor is more slippery, would it be okay for the ladder to go lower, or would it be better for it to stay higher? Right? So if the floor, if the floor has a certain amount of friction, that it'll kind of has something to push it there and keep it in place as the wall is pushing on here. Okay, so if there's less friction here at the bottom, then would it be okay? Because as that angle gets smaller, that normal force gets bigger, right? Or so it seems like if this were slipperier, I would expect I would need to put the ladder up at a higher angle, not at a lower angle, right? So if that floor is slippery, then I'm expecting that ladder might slip off that way and fall on the floor if that floor were more slippery. Well, if the floor were more slippery, us is in the denominator, then I'm saying theta is the angle whose tangent, this us got smaller, this whole thing then, the argument of the arctan got bigger, right? So the arctan of something bigger means theta is bigger. So this theta being bigger means the ladder's up kind of closer to the wall. So I would argue this answer makes sense in that way. Okay? Are there some questions about this one? And I don't see the chat, so if there's something in the chat, you'll let me know, right? Oh, I see some things have built up in the chat since I was last looking at it. Okay. Let's see if there's anything relevant to this last problem. Oh, someone has calculated it out for us. Thank you very much. And people are saying higher and bigger, and that's correct. Yes. Yes, very good. Okay. So I would say to everybody, Gokuro-sama. You worked really hard today, and I know it's kind of hard when it's such a nice spring day out there. I had just some parting things to let you know. If you were wondering about how moment of inertia by integration works, this morning in the morning section, they actually went through a moment of inertia integral. So if that's something that you would like to know more about, it's not going to be on the quiz, but it would be something that if you're just interested, I think they did a nice job of kind of laying it out. It's the kind of integral you might be asked to do in Calc 3 or Physics 210 if you're an engineer. So if that's something you would like to do, we didn't really have time in this section to do it, but the video is up. So please feel free to just go and take a look at that video. If you would like to see another statics problem worked out, they did a different statics problem in the morning section today. So there's another one on that video as well. So if you're feeling kind of iffy on the statics problems, that would be another place to see one worked out in the morning sections video for today. Okay, and just kind of as a parting thing, I went outside. It was such a gorgeous, gorgeous New England day today, and I took some pictures in my yard. I have a lot of forsythia, but I love forsythia. I don't have pets. I don't have kids at home anymore. So I have a beautiful garden with lots of flowering plants. So the forsythia are really, I think this is how you pronounce it, or how you spell it, forsythia. It's just in full bloom, and it's really grand. And I've got a garden full of various kinds of daffodils, and they're looking really, really nice. And the tulips are just kind of starting to, they haven't flowered yet at all because they always come up, after the daffodils. And then this is a really small plant called a violet, and my yard is full of violets. It grows in among the grass. So in New England, these are some of the big signs of spring, and I wanted to share those with you because I can't give you something homemade to eat, but I can give you something of the view I have out my window, and especially if you're not in New England at this time of year, it's just really beautiful, and I wanted to share that. The other day I was over on campus, and if you've been here in the spring before, you may have seen this, but I took a picture here. This is McConnell, and this is Bass over here. And this is as if you were leaving Burton from your math class and walking over to Ford Hall for your engineering class, if that's your major. It's that walkway in between McConnell and Bass, and it was just lit up with these beautiful trees. They're called rosacea. They're not that rosy in the sense that they're not very red. They're just a really light pink. And then there's this one is kind of purpley. So I wanted to give you, if you haven't been at Smith in the spring, next spring, I hope you'll get to enjoy all the flowering trees that we have and flowering bushes that we have at Smith. And my last thought for you is that it has just been a real pleasure for me to watch you all bloom since I put all these flowers up and grow over the course of the semester. I've really seen your physics knowledge and your physics skills, physics knowledge and skills grow this semester. And that's not just the people in my section, it's everybody that I've gotten to interact with from the morning section as well. So many of you will be at Smith for more than another year, some of you for probably 3 more years. Do not be a stranger. When you're back at Smith, you know where my office is in McConnell, and you know what my email is. And remember, physics has the best toys. So when you need to play, come to physics. It's been really, really great getting to know all of you, and I look forward to seeing you in semesters after this, maybe in another physics course, or maybe just looking for some help on a project you're doing for whatever course you're looking at. Okay? All right, take care of yourselves. And I'm happy to stick around for questions. I know Travis actually has office hours right after this. So Travis will be around for questions too, if anybody would like to say. Yeah, I think I should probably stop the recording part now.
Thank you.
Oh, you're very welcome.